On the end, I made it. We can see here the source code where it is calling. This is the source code. This is assembly compiled form, and this is the source code. We can see that the source code is a little difficult to understand because it has a lot of macro expansion. We can see that the function here is making in red. The system compares if a pointer in the buffer exists, it simply calls it here. Okay, if the pointer is not null, it simply references it and jump. Because why the system is doing it? Is doing that. It's a very common very common way to manage memory buffers. That it needs its own memory manager, and so in the same buffer, the structure, the header, got a pointer to a destructor, to a function used to free that buffer. It's used in a lot of places. In the Samba system, is a very similar structure. I don't know what protocol used this instruction, but there are, so I used it, and the exploit worked. I send a packet here, the system got us a pointer for the packet and jumped to it. So really, we jump wherever we want. It's not so easy, because where we jump. Well, here in this picture, we can see how the packet is sent. Here are the buffers in the memory. The buffers are consecutive in the memory. Every buffer, every mbuff, got a header that says a lot of things, says where is the next buffer, the type of the buffer, and inside this header is this pointer that say if the buffer has a custom destroying function. So we overflow from here on, and only we must place a trampoline. Trampoline is called a pointer where we want to jump. We place this pointer exactly in the position of this pointer here. It's always null, but we can control it, so we put a non-null value where we want to jump, and the system only jumps to it. We can see that, well, maybe it's a little small. We can see that there are the couple of packets I need to send. The packet was a fragmented packet because OpenBSD system get confused with fragmented ICMP packet. The packet must be valid because the packet must be processed by the system. And here are the header of the ICMP packet. A little lower, they are the pointer to our function to jump. And here is the payload of the shellcode, because we know we can jump every place in the memory, but we really need to jump to our code, because it doesn't matter if we jump to the same OpenBSD kernel or another place in the memory. We're crashing the kernel. We need to jump to our code to execute our code and compromise the system and make the system do what we want. We must place our code someplace in the memory to jump to it. So it's a little difficult to find where the shellcode is placed in the memory. So we simply place next to the trampoline. We put our code. So the code is placed in the next mbuff. We now jump to a place in the memory, and next in the buffers are placed our shellcode. Our shellcode got malicious code or code that we want to execute. So we really didn't know where we are, because the mbuff, the buffers, are in a position of the memory that we really didn't know where they are, because there are thousands of these buffers. They are constantly changing the position, so we must find where our code is placed, because it can be placed in a lot of position of the memory. How we find this? Where? how we find where our code is placed. We need to find where our code is placed to jump to it. Because if we jump to another place, the system crashes. This is what's called a one-shot exploit. If we jump to a place that is not exactly the location of our shellcode, the system will crash and the exploit will fail. We must jump. We got only one chance to jump to the position of the shellcode. I was saying before that the buffer was in the ESI register. So we know that our code is in this position of the memory. If we don't know where it is, but we know that the buffer is placed in this register, and then we jump to every place. So how we jump to our shellcode? We must find a special instruction in all the kernel that jump to the ASE register, because we know that the ASE, maybe I saying something in Spanish. We know that the ASE register got the position of our code. We only must find in the world memory, the whole memory of the kernel, an instruction to jump to the ASE register, to the ASE register. This instruction is very easy to find because it's a simple instruction. It's placed thousands of times in the kernel. So we simply will find where is this instruction. Is in a lot of times of the kernel, in a lot of places of the kernel, is used a lot. So we jump to this instruction, and this instruction we bounce to our code. We jump to the ASE jump code, and the code we back to exactly where our code is located. There are a little problem with this, is that we must jump to exactly the place where this instruction is placed, and this place might change for version of the OpenBSD kernel. Maybe a kernel, the instruction is placed in, I don't know, a direction, and then we recompile the kernel, and this instruction, it changed a little bit, changed maybe 1 byte. But if this instruction changed 1 byte, we want to jump to nowhere, and the kernel will crash. So we must find an instruction, a jump ASE or call ASED, call ASE, that is placed in the same position in all the kernels. It's a little difficult to find, but there are instructions that are placed in the same position. In the first part of the kernel, it's changed very little because all the change of the kernel I made, and the kernel, when you recompile the kernel, it really didn't change the first byte of the kernel. So we must jump an instruction that is placed in the first part of the kernel, and it will work the majority of the time. So we are jumping to this instruction. We are on our shellcode. We got here, got in the drawing. We know that this is all the kernel memory. We really don't know where we are, but we know that the ASE register is pointed to our shellcode. So we must jump to this place, and there is another problem. This exploit had a lot of problems. It's very difficult. That is because we are executing it in kernel mode. It's not like another exploit or another similar programs that are executing in user mode. But when we are executing in kernel mode, there are a lot of functions that we cannot do. We cannot simply access the hard disk. We cannot access the network. A lot of things we cannot do because we need the kernel for that, and we are in the kernel. If a user mode exploit simply makes system calls or make interruption. In Unix, the interruption used is the int interruption 80. To open a file, we just call the kernel. We say, hey, kernel, open this file. Or kernel, open this connection to the internet. But we are in the kernel, and in a kernel, but that we don't know what kernel is. Maybe it's the OpenBSD 4 or OpenBSD 3 kernel, 3.8 or 3.9. So we can't use the kernel function. We must do everything in the shellcode, like if we were a little operative system. So we must place our shellcode in user mode, because in kernel mode we can't do anything. We must find a way to place a little code in user mode, because it's much easier to exploit this way. So let's find a way to place our code in user mode. How we did it? Well, on one of the few things that we could do in kernel mode is to hook interruption. We can hook hardware interruption or software interruption, because it's very easy on the Pentium processor to find the interruption table. It's only a couple of instructions. So we say, well, what if we hook the system call? What if we hook the interruption 80? So every user process gonna call, when every user process will make a system call, in fact, they are calling us because we hooked this interruption. Like in the old DOS terminate and style resident program, in like 10 years ago, there were a kind of program that hooked the timer function, and this way they remain in memory. Well, we do it exactly the same. We hook the system call. We first found the interruption table in memory, and then we say, no, now the interruption 80 is us, and the shellcode, or us, call the kernel, and the kernel returns. But it's like a man in the middle. We are in the middle of every system call. You can see in this drawing, first the normal system call, make a int 80 and call the kernel, and the kernel returns to the user process. But we are made a hook, and the system, or the user process, call our code, and our code call the kernel. So we are intercepting every system call now. So we are gaining a little more information. We now can intercept every system call of every process. This, of course, makes the system a little slow, because we are we are injecting code in every system call. There are thousands of system calls per second in a running system. So here are hooking every process. In this way, we can override. By example, we know that some process is calling us, and we can override the return pointer to this process, so we can make the process we can make the kernel to return to every place of the process. But we really need a process. We really need a process that got administrator privilege, that got high privilege, because we are now intercepting every process. The printing process, the send mail, Apache server, and we need a process that got a lot of privilege, got a root privilege, because if we intercept a process that really didn't have privilege, the exploit is of low value, because we really couldn't do anything. So we must find if the process calling us is a root or is not. This is not simply because, as we are saying, we are still in the kernel mode. We are still executing in ring 0 here. We must find if the process calling us is root. So how we find this? We can